Gee, somebody should have, right. Okay, I better say what I was saying. The grader, I finally was able to reach out to him, and poor guy, he was in the hospital, and the hospital, he had some symptoms, and they finally checked that they did two tests, and they were both COVID-19 negative, but he did have things like a flu symptom. Anyway, now he's at home, so he's able to do his job. But I warned him, do not do the job online and then without realizing it, click on clear attempt. Because if Blackspot, you clear the attempt, that means there's no record of your attempt. So I said, be careful. What he did is to download all of the tests, and then he himself on his own computer does that little bit of partial credit. Basically, there's not much partial credit he can give. I have already done the major part. So he will check with me by sending me the spreadsheet and I'll compare. But basically, there won't be that much of a difference. Maybe you get an extra 3 points here or 4 points here, but that's about all, right? Now, as far as opting in or out, if you did better than the average, you say, I want to hang on to it because I did well. Why should you punish me by throwing away test one? So I say, yes, you can opt in which case then you'll be counted with 3 midterms. But if you say, well, I didn't do well because it was quite confusing. I had difficulty with this and difficulty with that. I don't dispute that. You can then work on just simply 2 midterms. And then your grade will be counted on 2 midterms, and there will be less chance of, you know, improving drastically from one test to the next. But in any case, the deadline for opting in, you have to inform me that you want to be opted in so that I have a record of it, so that at the end of the semester, I will in fact include all 3 versus just 2. Okay? And the next 2 tests by department college policy, you have to be live in person, and the proctors will sign you in. If you do the test online, it will not count. I mean, you you have to be live in person in MR3, and you do the Blackboard exam. Somebody had a question I didn't see.
Oh yeah, we were just wanted to know because you didn't say like a date when you want us to email you by for if we want the first exam to be counted toward our grade.
Right. So, but certainly it should be before the next test. So maybe let's say by next Monday. I hope that the grader has now settled with me. By next Monday, I will tell you what is now the average score. But we already, according to my way of looking at it, it was already, what was it, 100 and I forgot. Do people remember what it was? The raw score was 107 something. Now, if you did, according to the raw score now, you did 140, 150, then you say, how could you kill my test one results? So you want to opt in, you send me an email, then it will be opted in. All right. If you don't by a certain time, then basically I will now then say you are not counting test one, you're only doing test 2 and 3. Okay. So if you are opting in, you email me. Okay.
Okay,
Any
so
other questions?
so by next Monday we should email you, right?
Yeah, I mean, well, assuming that our grader didn't did not collapse. I mean, we should not,
Oh my
we
God.
should wish, yeah. I mean, you are the biomedical people, so Your job is to save people and not say, hey, I don't like you, out you go. Okay.
Could you send us an email when the grader
Yeah,
finished with all the
that's
tests?
right. I will then give you the updated raw score, but right now it is 107. And whatever raw score you know on the blackboard, you know what it is. Okay. All right. Any other questions? Okay, so now we need to now go on to chapter 24. Chapter 23 is for electrical engineers where they are designing a circuit and then they need to know what's the effective resistance with this AC circuit and so on. It's not for you and it's not for me. I'm not interested in those things. But we now come to a very interesting chapter because it involves electromagnetic waves and actually it affects our daily life very much so. So we need to come into it. Are you okay with this now? I'm still live, right? You can hear me?
Yes.
Yeah. Okay. Okay, good. Thank you. So now, if I have a wire like antenna, because basically when you have electromagnetic waves, you are basically asking for antenna for sending out signals and antenna for receiving signals. Well, if you have an antenna, you have a wire, right? I mean, antenna is basically a wire, and you have some current flowing through it, and this is an AC you're emitting. So it is an AC current. The signal is an AC signal. So if you start off with, let's say, one where, with an AC current, there will be a time when it is zero. There's the time when it's building up. It's the time when it is coming down and so on. That's how you get this oscillatory sine wave. So at time t equals zero, no current. But then at the later time, there's a current. All right. At a later time, there's a current. So there's an arrow, current going up. Now, current, you can think of it as plus charge flowing, even though Ben Franklin didn't quite know it at that time. Current is not positive charge flowing this way. It is negative charge electron coming down this way. But anyway, we have all been sort of used to this convention that the current is positive charge flowing, even though in reality it is negative electrons flowing downward. Anyway, when you have positive charges flowing this way, which way is the direction of the electric field? I'm being fussy now because I'm looking at this graph and I'm being fussy. Did Wiley Plus make a mistake now? Because I keep looking and say, hey, Wiley Plus, I don't trust you. Did they correctly give the picture of the electric field when a current is flowing upward? And the current is now beginning to go upward, right? Is this correct? I need your help. Which way is the direction of the electric field from a positive charge? It's like from your test one, you have to remember the electric field lines, right? If I have a positive charge over here, because now there's a current and all of a sudden in my wire, there's a positive charge now, right? Which way is the electric field from it? Downward. Thank you. So I say, okay, Wiley Plus, I give you credit now. Huh? Somebody says, what? Yeah, it is downward, right? So the electric field from the positive charge flowing upward is downward. So as this increases, the electric field gets bigger. And then it comes downward, and it is now the opposite side, and the electric field is now upward. So the electric field is now oscillating outside this wire. The electric field now was down and then up and then down and then up. So this is now the wave of the electromagnetic wave that comes up. Are you okay with this? All right. So now we're being fussy. That's because we already know the concept, and we say, yes, I understand now. If there is a some AC reason, because my phone, it has made my voice go into signals, and then the signals become the alternating current signal in the antenna. So I now have an electric wave coming up. But we also learned from chapter 20, what was it, 22, that there's a magnetic field due to this current, right? So we have to say, but I also remember, and whose law is this? I forgot. Can somebody help me? Is this Coulomb's law that say that if there's a current, there will be a magnetic field? Somebody's law. Nobody can remember? It's one of those guys, right? Faraday is electromagnetic induction inducing an EMF. But when there is a current, then Monsieur Ampere, Christian Ampere, that's why it's called amperes, right? When you have a current flowing, there will be a magnetic field around it. The current will generate also a magnetic field. And the same current will generate electric field. And I'm being fussy, and I add now to the same antenna, for the same thing that is emitting, there is a magnetic field that goes around by the right-hand rule, but there's also electric field, because these are positive charges flowing away, then the electric field from it is downward. So there is an E field downward, there is a B field sideways. All right? When you have an electromagnetic wave, there is always both electric field and magnetic field. When you have a current flowing in your antenna, there will be magnetic field. That is Ampere's law. But there's also electric field, because that's what Coulomb already figured out, that for any positive charge, there is electric field directed away from the positive charge. So since this is going this way, the electric field is downward. Therefore, this antenna has produced an electromagnetic wave with electric field and magnetic field. And the electric field and magnetic field are perpendicular to each other. That's the key concept. The Ampere's law says if my thumb is the direction of the current, then the magnetic field curls around this thumb in this direction. Therefore, the magnetic field is always perpendicular to this current. But the electric field, is always in line with whatever is the current. And if this is the current flowing up, the electric field lines are coming down. So I have now a certain orientation. My electric field is always perpendicular to magnetic field. All right? Okay. Are you okay with this concept? Because we need to grasp this concept. It will be very important when we talk about the signals that come out from the sun, the signals that come out from your radar, the signals that come out from your handphone. Well, it is electromagnetic wave, and it is one where the electric field and magnetic field, they are always coexisting and they are perpendicular to one another. Okay, is that key concept now clear? That's why we call it electromagnetic wave. Okay, so now this shows a picture. This shows a picture that I have an antenna here, and this antenna is, of course, sort of alternating current, so it goes up and down and up and down. And now these will emit, they will emit electromagnetic wave, and the electromagnetic wave will now always be in sync, in the sense that when the electric field is up and maximum, the magnetic field is also maximum, but sideways, perpendicular. Do you see this picture? And then when the electric field flips over, well, again, the magnetic field also flips over. And one thing you will notice, the book did not emphasize it, but later somewhere they should emphasize it, that if I take this hand, E cross B gives me the direction of wave travel. E cross B. If you have your right hand and you now take this guy, E is upward, B is out of the board, then E cross B gives you the direction of propagation of the wave. All right. So when anybody reproduces a picture like this, you can check on whether that person who gave you that picture, that graph, is correct or not correct by checking, is the propagation, the direction of wave travel, indeed given by E cross B. Just like later when you talk about the rainbow, the primary rainbow and the secondary rainbow, I will always want to tell people the order of the color. Red, Roy gives red, orange, yellow, give green, indigo, violet, that the order of the color for the primary rainbow is opposite from the secondary rainbow. And if anybody shows you by Photoshop a picture of beautiful, double rainbow over Rio de Janeiro, if you look and see whether the secondary rainbow, the color, the order of the color is reversed from that. If it is not, that means somebody, what they did was to Photoshop, take a primary rainbow, make it bigger and superpose on the other one. So just be careful. Okay, am I making too much noise? Okay. So this picture shows the wave of the radiation field far from the antenna, because this antenna has radiated. That's the word that we begin to now use. Has radiated this electromagnetic wave, and it is traveling across space. Now you notice that when we say that we have electromagnetic wave crossing space, we did not require a medium. When we talked about the sound, you remember we say, I am able to communicate with you because my voice here is pressing against the air. And you have compression, decompression, compression, decompression. So you have a longitudinal wave propagating. And then the compression, decompression impacts on your eardrum. And when your eardrum gets compressed and decompressed, compressed, decompressed, it sends a signal to your brain, and you say, oh yes, now this professor is crazy. He is waving, but there's no sound. Why? Because he forgot to turn on the mic. But anyway, you then get this through the medium. And if there is no air, then there is no sound. You will not hear anything. Your mic may be, vibrating, but you will not hear anything because there's no medium. But electromagnetic does not require a medium. This is empty space. You are now doing your AC generator. You are now providing the signal, and the signal will now travel with this E cross B, giving you the direction, and it is now going all the way from the sun to the earth, all the way from the galaxy to the earth, all the way from the supernova to the earth. So this is the one very important feature of electromagnetic wave, that you do not need a medium. You do not need air. You do not need water. You do not need any kind of medium. And there's a very important discovery. We don't have, maybe at some point we will get into the sort of little bit of history in behind it. But you remember Sir James Clerk Maxwell. He took Ampere's law, he took Faraday's law, and then he knew enough mathematics, which you remember Faraday did not really know. His knowledge of was not much beyond algebra and trigonometry. But anyway, Maxwell, he was able to take Faraday's law and Ampere's law, and then formulated the mathematics involving Stokes' theorem and Green's theorem and so on. You are not mathematicians, so don't worry. You will not be asked to memorize that. But he put them together, and voila, he discovered that electromagnetic is a wave, and this wave therefore has a wave velocity. And furthermore, he was able to calculate the velocity of this wave to be 3 times 10 to the 8 meter per second. This is the fastest speed ever that we know, any phenomenon. This is the fastest speed. All other speeds that you know, whether it is sound wave, water wave, tsunami wave, etc., is nothing compared with this. This is a fantastic number, 3 times 10 to the 8 meters per second. All right. And now a radio wave that is coming all the way from the satellite, the GPS. The radio wave that comes from it, electromagnetic wave, it will now induce, because now I have an antenna. It's sort of the opposite of the other one, which was generating this wave. Now I have this antenna, and this antenna is there waiting. And when your wave comes by, the electric field here will now say, hey, the current that will be induced due to this electric field is downward. You got it? Right? Because the electric field is upward, pointing upward, then the current that will now flow is downward. And the magnetic field, they only showed the electric field. They didn't show the magnetic field. The magnetic field would have been this way and this way. So there will now be an induced current, and the induced current will now oscillate according to your frequency. If this frequency is so many gigahertz, megahertz, then the induced current would also be gigahertz, megahertz. And that's how you then are able to receive a radio when somebody is singing. You know, I don't know what somebody would be singing today, the nice weather. I don't know what kind of song they would sing. Well, then you have different frequencies. There will be a part of the wave which is at so many frequency, and the composition of it all is what your amplifier circuit now would now be detecting. All right, is this clear now? You generate it, it now propagates, and now it comes and it induces by induction a current, and this current now makes my audio amplifier now with my mic in there, and the mic will now start vibrating according to the frequency, and then I will say, oh yeah, that was a particular note, a C note or a whatever, A note and B note and so on. I'm not a musician. Are you okay with this picture now? Okay. But now, oh yeah, now then they first showed only the electric, but they also now show the magnetic. You got it? And they are correct, because if this E is up, then B should be this way. So they are this time correct. So now, as far as the magnetic field is concerned, it can also be used as a thing to induce a current. And this will now, in the loop, will have a certain current. And again, that's what, so your antenna can be a loop, or your antenna can be a just like a wire. And different applications, they may use different designs. The engineers have, of course, over these last 300 years, designed many different antennas. For the phone, it's sort of like hidden. You don't see the antenna. It is hidden somewhere. I don't even know where, but it is hidden. But for those reporters that are in, Afghanistan, or they need a thick antenna that sticks out from the phone. And then they would be now talking to this, and this big antenna sends the wave all the way to a geosynchronous satellite, and then that signal comes back down to CBS, NBC, ABC, right? So now that we can kind of begin to appreciate that electromagnetic is a wave, and it has a certain frequency, and it actually is a whole mixture of frequencies. Well, this is now a very interesting information that we need to grasp, and that is that this electromagnetic wave can be of any kind of frequency, can be of frequency that are very, very high, more than 10 to the 24. In fact, there's no limit to it. It really depends on your original source. And when you begin to get into astronomy, you begin to also hear about this Big Bang. And when there's a Big Bang, there was truly a big explosion, although it's not like a thunder explosion, but it is really the whole space is created. And you now have very, very high infinite frequency and very, very low frequency, because you notice this one is 10 to the 12, 10 to the 8, 10 to the 4, 10 to the 2, 10 to, it could even be very low frequency. And this is what you call the electromagnetic spectrum. It spans a very wide frequency range, but what we see, I am able to see you. Well, no, I cannot see you. All are all just little dots on my screen, but you can see me. When I see the table, when I see the lamp, when I see this, I am using a very small portion of the spectrum. And this is what you call the visible light spectrum. It's only over here. And they have sort of expanded it. And they are saying, hey, the visible spectrum is from frequency from 4 times 10 to the 14 to 7.9 times 10 to the 14. It's a very small part of this spectrum in the range of 10 to the 14. And then in this range, there is the red light, there's the violet light, and this is where, depends on which way you want to read it, Roy give, red, orange, yellow, green, indigo, violet, right? Roy give, or Vitgyor, violet, indigo, blue, green, yellow, orange, red. You remember those Roy give or Vitgyor? It is just simply the range of colors, right? When you see the sunset, it's mostly all red or orange. But right now we see the blue sky. Well, it has to do with Rayleigh scattering, but later, I don't know, is this in 204? You will learn about light, or is it in 20? Yeah, probably there will be there's a part where you do light. And then we will sort of ask, how is it that when it is sunset, the sky becomes red, but otherwise it is blue? But we will leave that to later. Now, for our daily life, apart from the visible light, there's also the very important radio, right? And microwave. If you don't have microwave, oh, you will have difficulty in having a quick, something to be, you need to cook something quick. Well, microwave is what you begin to use. Well, microwave involve electromagnetic waves in this range, whereas AM and FM are the radio waves that we use. And this is the band, and the FCC, I guess, they control. For ABC, you get this particular frequency. For CBS, you get this. And so they sell this, the right to the spectrum. Okay, now, like always, electromagnetic waves have a wavelength and frequency. And because it is a wave, we have this fundamental relationship. Because they all, it doesn't matter what frequency they all have the velocity of light, 3 times 10 to the 8. Because they all have 3 times 10 to the 8, their frequency, if you tell me what's the frequency, I know what's the wavelength. If you tell me what's the wavelength, I know what's the frequency. They are not independent of one another. If it is 10 to the 24 frequency, then the wavelength has to be 10 to the minus 16. If the frequency is 10 to the 4, then the wavelength has to be 10 to the 4. Why? Because the product is 10 to the 8. All right? Any comments or questions at this point? Okay, now let's do a little exercise because it's a good exercise. They say, what is the wavelength of visible light? Find the range in wavelength for visible light in the frequency range. 4 times 10 to the 14 to 7.9 times 10 to the 14. Well, we can just do the calculation. You just say, I know the velocity of light is 3 times 10 to the 8, and you told me that your frequency is 4 times 10 to the 14. Voila. The wavelength of the light is 750 nanometer. And it is good to know that is red. 700, around 700 nanometer is red. Now, you say, but my frequency of light that I am now seeing is 7.9 times 10 to the 14. Well, it is about 400 nanometer, and that is violet. And the range, red to orange to yellow to green and indigo and violet, they then just say that the wavelength is between about 400 nanometer to 700 something nanometer. All right, and now the book gives a pose an interesting question. I have AM station and I FM station. Now, have you noticed when you are driving and you have a AM radio or FM radio, which one is what you call more easily bothered, or when you're driving in the city, that's a better way to say it. When you're driving in the city with all these buildings, right? Which reception is better, when you have AM radio or when you have FM radio? Huh? Do you listen to the radio even as you don't drive? Have you noticed any difference between AM station, FM station? Yeah, you don't drive. Yeah, no. Anybody has been in a, well, you may not drive, but have you been in a car or in a bus listening to a radio? Oh, you don't notice it. Huh? Which one is more easily bothered or affected by buildings? It's FM. FM is more easily bothered by buildings. You're coming across, and this is Empire State Building, and you're turning south to Fifth Avenue and so on. It's the AM station that don't seem to be that much bothered by tall buildings, but M is very easily bothered. Why? Okay, now here is our picture of AM and FM. AM has lower frequency, therefore it has, is it longer wavelength or shorter wavelength? The fact that AM has lower frequency, does it have longer wavelength? All right, and now AM waves, they are long. They are actually longer than let's say a building block. So they're not bothered because the wave is so long. The fact that you're here makes no difference to me. But FM, the wavelength is shorter. The wavelength is shorter. So then they are more easily blocked by your building. You see, I am a shorter wave, boop, you block me. But me, I'm a long wave, gee, I am sort of like, I can go around you. The technical word is diffraction. And when we come to light, we will learn about diffraction. But I'm now trying to give you a sort of like a child's understanding of this AM and FM. AM waves, they are long. Well, so it is, I am going like this, going like this. The fact that you are here doesn't bother me. So I can continue. You can continue listening to my AM station. But the FM, their wavelengths are short. And they are saying, oops, I got stopped. I will now have to bounce over here and go bounce over there, then it interrupts your reception. Okay. Okay. Now you remember Maxwell? He figured out, and maybe sometime when we have time, I don't know, I will sort of give you a quick run on how Sir James Clerk Maxwell figured it out. But when he first figured it out, that says that it is 3 times 10 to the 8 meters per second. A lot of the scientists, physicists around the world, and says, wow. And so it became a question. I want to measure it. Don't you want to measure it? Of course, you as biomed, you just say, I don't know how I could ever measure it. But physicists and scientists, they want to now measure. And then there began to be sort of like a competition. The people in Europe, they want to measure, and they say, it's not 3 times 10 to the 8 meters per second. It's 2.99 times 10 to the 8 meters per second. And then the other lab will say, wait a minute, I can do better than you. I measure it now, it is 2.9979. And then the other scientists around the world will say, wait a minute, I can do better than you. I can do it to 1, 2, 3, 4, 5, 6, 7, 8, 9 significant figures. And now in America, there is this scientist called Michelson. Well, Michelson was one of the first ones to actually do a good measurement, and he used a trick. I mean, it was not as simple as this one says, but the book says, okay, they will reduce Michelson-Morley idea to an easier one that you can understand. And what he did was, you have a light source, and of course light comes very fast, and now this light will be reflected off, and in this example you have a rotating octagonal mirror. All right, octagon means there are 8 sides. There are 8 sides to this, and now when this light reflects off to it, it will then go to this fixed mirror over here. Then it would be reflected back, and then it will now come into the observer. And now if the thing is rotating, then if my rotation is not in sync, when the light comes back, it will not come into my eye, it will be reflected off that way. Do you follow the idea? This thing is now turning, and if it is not in sync, your light went over there and came back, but when it came back, I was not in sync. I'm not in this orientation. I'm on a different orientation, because I am now like halfway instead of this way. Then the light would not be reflected into me, it would be reflected away from me, either over here or over there or over there. So I can now kind of tune this, and I say, I will make this either faster or slower, but I will make it such that, hey, I see the light. And then it becomes a calculation. There is a certain time delay, whatever is the distance, and they say it's 35 kilometers, whatever is the time delay, I have now found just the right angular speed so that this light will be reflected into me, and therefore I know the time delay. And since I know the distance, I know the speed. Are you following the crude idea here? Are you following the crude idea? Okay. Now, Michelson-Morley was a little bit more sophisticated than this, but anyway, this is sort of like the idea that you can figure out the time delay for this light signal to go from here to there and back, because you have synchronized it just right, that, oh, I see the light. But if this is out of sync, uh-oh. And since I now know what is the time in my sync, because I know my angular speed, I can therefore measure. And Michelson-Morley was one who sort of first did. I don't know how many significant figures, but they did it. Okay. Now, there's another application of the fact that this is a electromagnetic light that has a velocity, speed. Oh, I didn't mention this. There was this crazy competition from one lab to the next lab. Then at some point, they all say, hold it. How do you know what is 1 meter? And if you remember from your 203, a meter is the length of a meter stick, a bar, a bar in the vault. Well, I have a ruler here, a transparent ruler. But anyway, there's a bar in the vault in Paris. And then they say, that is what a 1 meter is. And that has to be kept at standard atmospheric pressure, at standard temperature of 20 degrees Celsius. And with that condition, this is 1 meter. And then all the manufacturers, the National Bureau of Standards and so on, they all come to this vault in Paris, and then they measure, and then they say, okay, that's your stick. I now measure it, I bring it home, and then I have it in my vault in National Bureau of Standards. And then all the manufacturers of these meters, they would then go there and say, yeah, now my meter is 1 meter. And then somebody will say, how do you know that your meter stick is indeed exactly 1.0000000000000 meter? At some point you say it's kind of silly. And so there was an international convention that says, oh, you now define, you say the speed of light is by definition 299,792,458 meters per second. Then any other distance, how far is this from here to Albany? Oh, you just tell me how long it takes the signal to reach you, by light, that is, by electromagnetic. If you tell me that the signal took 0.005 seconds, I just say, your distance is the velocity of the light, because that's the signal, radio signal, times the time, that is then your distance. So the distance now is now defined in terms of your velocity of light times the time. And then the time is by the atomic clock, which is cesium and so on. But anyway, this is how the scientists sort out this. Okay. Now, here, this is a very interesting one. This has to do with astronomy. A supernova is a violent explosion that occurs at the death of certain stars. We don't want our sun to die, because if our sun dies, we cannot live, yeah? Well, a supernova is a violent explosion that occurs at the death of certain stars. And this is a picture of something called Tarantula Supernova. I'm not an astronomer, but NASA says that they have observed. And this is a supernova. Why? Because they have been staring at this galaxy, keeping an eye on this galaxy, and then one night they suddenly see a, what you call a light, a sort of a real explosion, that something became very bright. And actually there are these supernovas that are bright and pulsating. But anyway, they just discovered that, there is this Tarantula supernova, and they are they are able to say it is so far away. Now, it is the astronomers, they have spent years of comparing a supernova in our Milky Way with other nearby galaxies and so on. So they have worked out I guess, a knowledge of how far something is. You know how? Because by the intensity of the light. Because they know a supernova, when it explodes, will have a certain, what they call candle power. You know, like if you give me a standard candle, I know what its intensity of light. Later on, we'll talk about intensity of light. And I know that if I am 3 feet away, the intensity is so much. But if I am 6 feet away, the intensity would be a quarter of it, because it goes down by inverse square law. And so they now say, hey, I saw this, but its brightness is, compared with the other one that I know that is nearby, because it is in our Milky Way, it is less. And so by the sensitivity of my telescope, I now know that this supernova that exploded, it is 1.66 times 10 to the 21 meters away. All right. So they learn it by inverse square law from the intensity. All right. Is that concept clear? I'm teaching you astronomy now instead of biomedical, but enjoy it. Okay. You learn by the intensity, right? From the Milky Way, we know what is the intensity. We have measured it. And then now this guy that is on this corner of the sky, the intensity is so small, but I am very sensitive. NASA has very sensitive telescopes, so by Hubble's telescope. So I now know that it is 1.66 times 10 to the 21 meters away. Well, if that is so, I can then ask for that light to reach me. For me to see it now, it must have come and took this much time. Why? It is the distance divided by the speed of light, right? And so now I can now work out the math. I put in 1.66 times 10 to the 21 meters divided by 3 times 10 to the 8. I mean, we're not going to do 2.9979 and all that. We just say for order of magnitude. And voila, this one is therefore the light took 5.5 times 10 to the 12 seconds. 5.53 times 10 to the 12 seconds, which is how many years? It corresponds to 175,000 years. This Tarantula Supernova, it is so far away. And in astronomy, NASA now is very interested in, with the Hubble telescope, in looking at the furthest possible galaxy, for the furthest possible. And they are using these supernovas as candlesticks, because they know a supernova would have, given off this much power. So they use that as a candlestick to then say, wow, I'm able to look back in time, and the latest number that the astronomers give is that the age of the universe is 13.7 billion years. 13.7 billion years. And there's some scientists that keep trying to modify, try to do more of that. But anyway, that is what, using the simple application of these supernovas to now imply, assuming that the speed of light remains 3 times 10 to the 8 meters per second ever since creation that then it is 13.7 billion years ago. Okay, but now the book at least acknowledged that Maxwell's prediction was in 1865 and that the speed that he got, 3 times 10 to the 8, really came from this formula. How this formula comes about, it's a combination of Faraday's law and Ampere's law. Faraday's law has these permittivity and permeability. And you remember we had the difficulty with blackboard in the test one because epsilon 0 is very small. And then blackboard just says, ooh, it's so small, I just call it 0, even though the formula is 10 to the minus, I forget now, 10 to the minus 9 or 10 to the minus 12. So the blackboard just simply gave up and said it is 0. But Maxwell, he knew what was epsilon 0, he knew what was mu 0. Epsilon 0 is 8.85 times 10 to the minus 12 in these units. And mu 0, permeability, is this, 4 pi times 10 to the minus 7. If you put them together, you say C is 1 over square root of epsilon 0 mu 0, and that works out to be 3 times 10 to the 8. So that is how Maxwell figured out, because he was just dealing with mathematics. He was dealing with the Faraday's law and Ampere's law, and then use these Stokes theorem and Green's theorem, and so on. And he figured it out, but he therefore immediately figured out that it was 3 times 10 to the 8. Now for us today, what we need, apart from knowing that there is this wave nature of light, is we need to know how much energy is involved in this light. Because after all, the sun is the source of our sunlight. How much power came from the sun? Of course, the sun must have emitted a huge amount of power, right, by the light. It emits it in all directions. The sun is not one that will say, hey, I love you, Earth, and I will now only emit light in your direction, and I will ignore the rest of the universe. The sun is just a body, which is like a sphere, and so it will radiate in all possible directions. But we are on the Earth. We will pick up only a small segment of it, and we now need to learn something about how much energy is coming from the sun. Especially these days, we all are interested in solar power, right? Have you heard of green power? Have you heard of green power? Yeah, to be green, right? And so what you're saying is, hey, I want to be able to have a solar panel on the top of my roof and to receive the sunlight, and the sun has delivered this much power, and we will learn how much power it is. It's about 1,000 watt per meter squared. So if I know that the sun has delivered to me 1,000 watt per meter squared, I make my panel like a meter squared, then I will have a kilowatt. And for my house, I will need more than 1 kilowatt. So people have roofs that have quite a lot of solar panels, right? Here, this book just shows an example of a microwave. Oh, excuse me. Somebody, somebody read what the question was.
There are myths about microwave radiation. Is microwave radiation safe for our health?
Yeah, it's contained inside the microwave. You don't have microwave radiation when you open it because then it stops. Microwave, they are focused on the, what is this, the toast here, right? It is there to toast the toast. And it is only, whoops, and it is there when it's turned on only when you have closed it. The manufacturer for the microwave oven, they do not open it. The issue is sometimes your microwave oven, because you have been using it, opening it and closing it, opening it and closing it, that it is not fully closed. If it is not fully closed, some of the microwave radiation can come out. And now they are at a frequency range which is not good for our health. So just be aware of it, okay? You remember the picture where we had the spectrum, and then the microwave spectrum is below our visible range. So when your microwave oven is leaking microwave radiation, you won't see it. It's not visible spectrum. It is to the left of visible spectrum. So you wouldn't know. And that's why you better be sure that your microwave oven is indeed, not used for what, for 20 years, 30 years, in and out, in and out. That be careful. Just be careful. Okay. All right. So now we want to know what is the total energy. Somebody says that microwave can only vibrate water molecules. But Madame, Monsieur, are we mostly water? Is our blood water? Is our eye water? I mean, we have eye, right? So microwave affect the water molecules, but we have water molecules inside us, no? Or are you made of solid wood? Huh? Or are you made of solid whatever? No, we are made of blood flowing through. And so microwave radiation can affect us if we are exposed to it for a long time without realizing it. Okay, all right. So now let's go on now, because it's a question of how much energy is in this electromagnetic wave. Well, you may not remember this, but in chapter 19, there was this energy. Well, we didn't really go into how we derived it, but it was in chapter 19. It's the energy density. And in chapter 22, there's the magnetic field, and it has energy density. So now we want to make use and say, for electromagnetic wave, it has both electric energy density and magnetic energy density. They are always together. In an electromagnetic wave propagating through vacuum or air, because in this case, basically, we can think of air as like vacuum, the electric field and the magnetic field carry equal amount of energy per unit volume of space. That this, in terms of energy density, is the same as this, because E and B, they are always correlated. Well, therefore, 1/2 epsilon 0 E squared is 1/2 B squared over mu 0, or E squared is therefore 1 over epsilon 0 mu 0 B squared, right? Half goes away, and you move the epsilon 0 over here. But you remember, C is 1 over square root. Therefore, this says that E is CB. In these metric, in these engineering units, the system international units. So in terms of these units, the magnitude of the electric field, so many volts per meter, is C, so many meters per second, times B, which is Tesla. So with this, you now say the energy density, total energy density, you can now write as 1/2 epsilon 0 epsilon squared. And with this, you can therefore write it as either epsilon 0 E squared or 1/mu0 B squared. Namely, this equal to this. So you either double this one or you double that one. They are always related because E squared is C squared B squared. Okay? All right. So now we are ready to do a little daily life application. And the book has it. It's example 4. You have sunlight. It enters the top of the Earth's atmosphere with an electric field. And the engineers, the scientists, they have measured that the electric field, by the way, you remember what is RMS? Do you remember what is RMS? Root mean square, right? So therefore, this is the root mean square because the electric field keeps going back up and down, up and down, up and down. The maximum is square root of 2 times this. And the root mean square is 1 over square root of 2 times the absolute height of the wave, right? But anyway, they have made these measurements. And for them, it's important because a lot of all the screen power, the sunlight coming at top of the Earth's atmosphere, the solar constant is 1,074 watts per meter squared. I may be wrong, but it's something like, it's more than 1,000 watt per meter squared. It's like, I think 1,740 or something. Somebody can look it up. It's either 1,074 or 1,740. I should have looked it up. But the final amount of solar energy that reaches the ground is not the original one. Let's say it is 1740 watt per meter squared. The final one is only about 1,000. Why? Because the atmosphere itself is filled with oxygen, nitrogen, carbon dioxide, and so they absorb part of the solar energy so that by the time it reaches me lying on the beach at wherever, Coney Island, right? Then the amount of radiation that I see is not what it was at the top, which they call the solar constant. It is now only about 1,000 watt per meter squared. And furthermore, because we are not at the equator, we are over here in the latitude of 40, then it is not even 1,000 watt. It'd be a little less because it's cosine of the latitude. But anyway, I'm getting, what we want to now do is to just do a good, quick calculation of what is the average energy density of sunlight at the top, okay? So now what we do is we say, okay, I know the average energy density is epsilon 0 E RMS squared, which I can now figure out, and it is not much. It is 10 to the minus 6 joules per meter cube. That's the density per unit volume, okay? And now if you want to say, but what is the root mean square value of the magnetic field? Well, that's easy. That's just, you told me what this is. I now use the formula that says that magnetic field is related to the electric field by this factor of C. And so this is 10 to the minus 6 Tesla, which means that the magnetic field of this electromagnetic wave is smaller than the Earth's magnetic field. You remember? The Earth itself has about a third of a Gauss. The magnetic field, due to the magnetic pole inside our Earth, it is about a third of a Gauss. So therefore, this is small, but it's coming in constantly and it's free. You don't have to do a coal mine and get the power from a generator. It's free, but it is limited. Well, so now they want to do a estimate on this power, how much power is delivered to us by the sun. All right, how much power is delivered to us by the sun? Now we already learn or know by definition, total energy is the energy density times the volume. Well, here is this electromagnetic wave coming in, and now they are being good. They show both the electric field and the magnetic field. The pink arrow is the electric field. The blue arrow is the magnetic field. And when you say E cross B, it gives me, the thumb gives me the direction of this wave. Okay, so this is correct. It is now impacting on my whatever panel, whatever absorbing thing that I want to use to absorb, right? So I now say it is U, the energy density, times the volume. And the volume is CT times A. Why? T is the thickness. Therefore, no, T is the time. T is the time. CT is therefore the thickness. Why? Because this wave is coming in with velocity c. So in this volume, which is CT times the area, I now find what is the intensity. The intensity is the power that passes through the area A. The intensity, when you say, gee, there is intense heat, that means that there's a lot of energy being transferred onto me by the sun, by this radiation from the sun. All right. So you want to now say, well, the intensity, they call it S, because they cannot use I anymore. If you use I, it then means current, and you'll be very absolutely confused. So the intensity, they call it S for solar, solar intensity. The intensity is the power that impacts me per unit area. That's the intensity. And the electromagnetic intensity now is S equal to P over A, which is the total energy. Well, power is total energy over T. Power is total energy over T. You remember? If I did this much work and I did it in a short time T, I'm very powerful. So the power is total energy over T. But total energy was U CTA. And this is now over the time interval T per unit area. Therefore, by the time you work through this, the formula for the electromagnetic intensity is simply C times U. So it makes this concept of U very convenient. It tells you that the intensity of light coming from the sun is whatever is the energy density times C. And so, whoops. And so you can now do some exercises involving the numbers, because they will tell you, oh, I know what is the the electric field, I know what's the magnetic field, and therefore I know what is the total energy density, what is the intensity, and you have to figure it out. Okay? Any questions about this?
Professor, I just had a question about the regular constants. Are you going to give us the values during the exam, or do you want us to memorize them?
Oh no, you don't have to memorize all those constants. No. I will not say, oh, you better remember what is epsilon zero, you better remember what is mu zero, you better remember. No, I will, the blackboard will, and now that I know the tricks about blackboard, when I tell you epsilon zero is, what was it, 8 point something times 10 to the minus 12, I will tell you it is 8.9 something, and then I will separately say it is times 10 to the minus 12 so that you can see it. All right. So now that I know the quaint,
Thank you.
the quaint things about the blackboard, I will avoid the silly, issues that we had with test one. Okay. So you don't have to say, oh, I need to know the value of epsilon zero. I need to know the value of mu zero. I need to know the exact value of the velocity of light, which is 2.99792 blah, blah, blah times 10 to the 8. Okay. Any other questions? Okay, so now we have the electromagnetic wave. We know that it is a wave, and we know that it is a wave that involves electric and magnetic field, and the electric and magnetic field are always orthogonal to each other, perpendicular to each other, and their direction is E cross B gives me the direction of this wave. And we now know that this wave carries energy, and this energy density is what we call U, and this U is epsilon zero E squared, or it is B squared over mu zero. The epsilon zero is permittivity, mu zero is permeability, but they are numbers, they are constants. And so now we know, I also therefore know what is the intensity. So I basically have now a good sense of solar power. I know a good sense of the solar energy that comes in. And the thing that I wanted to, I guess I have already conveyed, is that it's good to be able to have solar power, but to really have enough solar power to replace all of the coal mine, you need a big solar farm. You need big area. Why? Because it's only about 1,000 watt per meter squared. 1 kilowatt will not supply you. We need megawatt. And so for megawatt, you need a big farm. And so in Arizona, they can have a big solar farm. But in New York City, you cannot expect to have a solar farm. So just be aware, although it is good to have the solar panels to keep individual street lamps, because now if you drive around some neighborhood on some highways, they actually have solar panel for each individual light. And so in that case, they are in fact making use of the fact that the sun is shining on this light pole all the time, and you can now store that light and use it to light the lights along your highway. Okay, so just to give you an overall picture. Any questions about? Okay, if not, let us now go to the Doppler effect. Now you are already familiar with Doppler effect from chapter, what was it, 16, right? Where you have the sound wave and then the actual frequency you hear when a train is coming towards you, when the train is coming towards you, is the frequency you hear because you are on the platform. Is the frequency now higher or lower? The train is coming to you. You remember test one? The train is coming towards you. Is the frequency you hear on the platform, is that now higher as it comes towards you? Yeah, thank you. But now when it passes you, what happens? When it passes you, what happens? It gets lower, right? And so you know about the Doppler effect. And then for sound wave, it also depends on what is your, if you are not stationary, but you are now moving, you remember you had to deal with the Doppler effect, depending on whether you are moving yourself, you're the observer and the source, and the source is moving and the observer is moving. You have to have it upstairs or downstairs. You remember all of that? But now one thing about electromagnetic waves also have a Doppler effect, but it differs from Doppler effect of sound. Sound waves require a medium, whereas electromagnetic waves do not. Sound waves require compression, decompression, compression, decompression. And if you're a car, you remember test one, you have a car moving to the left, then the distance between the compression and the subsequent compression is now shorter, right? But if the car is moving the other way, then the distance between the first compression and the second compression is longer, and you had to sort it out, and you have to put it either in the numerator or denominator. But electromagnetic waves is easier. It does not depend. For sound, it is the motion relative to the medium that is important. For the electromagnetic waves, only the relative motion of the source and observer is important. If you have the source and you are the observer, well, you have 1 plus minus your velocity relative to the velocity of light. And now, which one should we use? When do we use plus? You're the source. You're the distant star. And you are now moving towards me. Do I use 1 plus or 1 minus? Thank you. You see, you already have the sense of Doppler effect because you have experienced it all the time. You hear a train passing by, you then know it is coming towards you or leaving you by the frequency. So this then says that if the sun, which is the source, right? Fs means the source. If the sun is now, well, not the sun, let's say it's the star, galaxy. If the galaxy is now rushing towards us, well, then the observed frequency will be higher. Now, you got to be a little bit more precise. I have to know what wavelength you're talking about. I have to know that this is red light. If this is red light, then I already know that if this, you're the source red light frequency is, I forget, blah, blah, blah. Or the red light wavelength is 700 and, what is it, 790 or 740 or 750 nanometer. Somebody had a question, I didn't see it. I didn't see the question. No?
It says, is this equation is for a moving source?
Yeah, for a moving source, and I'm the observer. And whether it is plus or minus depends on whether you're coming towards me or leaving me. All right? But now, this also applies if you are stationary and I'm running. If you're stationary and running towards you, it's the same formula. I'm running towards you, you are stationary, but I'm running towards you, then the frequency, you see, you are the source. Let's say the source is stationary and I'm running towards you and I'm the observer. Then I will also find that it is now plus. You got it? So whether you use plus or minus, you just simply view it from the point of view of the relative motion. You may be at rest, I'm running towards you, then the frequency will be higher. Or you can be running towards me and I'm running towards you, right? Then the frequency I observe, I'm the observer, will also be higher, but it would then be 1 plus the relative velocity. But in this case, the relative velocity is twice, double, because you're running towards me, I'm running towards you, so our relative velocity is now double. Is that easy to understand? All right, so this V relative is the relative velocity between me and you. You are the source, I am the observer, and if you are stationary, the relative velocity is my velocity. But if you say, I hate you, or no, if you hate me, would you run towards me? Maybe, yeah, you want to hammer me, right? So you're running towards me, and I'm running towards you. Well, the relative velocity now is double because you are coming to me and I'm coming to you. So the relative velocity is double. It's the relative velocity, and then it's 1 plus. But if you are running away, then it is minus. So this is then the thing about Doppler effect for electromagnetic waves. And again, we have this. And now, the plus sign is for when the source, when you are coming together, and you can have the source is catching up with the observer, or the observer is catching up with the source, or the source and the observer are both moving towards one another, as I said, right? So for electromagnetic waves, Doppler effect is very easy until you use relativity into effect consideration. Then you need a little bit more understanding. But here, the velocity is not that big relative to the speed of light. For relativity, then special relativity, then you have to do a little bit more, much more sophisticated analysis, right? So here it says you use the plus sign in any of these situations because all that matters is that we are now coming together. Minus sign, now that is when you are moving apart. The source is pulling away from the observer, or the observer is pulling away from the source, or the source and the observer don't like the smell from each other and they run away from each other, right? They both move away from one another. Then you say that you use the minus sign. Okay, so applications involving Doppler effect is actually not difficult. Any question? Okay, so now it's a interesting application here. You have a, you must have seen this. You are speeding. How does the police car know you're speeding and are able to figure out your speed? And nowadays, in some of the country roads, they put a radar detector down here, and then it shows, it will say, you are now going at 37 miles per hour. You are now going at 40 miles per hour in a 35 mile per hour zone. How do they know? How does that board, have you ever seen that? You don't drive it in your, I don't know about New York City, but in Teaneck and other suburbs, in some roads, they usually would put a some sign like that, which automatically lights up when you come by. There's no siren, there's no nothing, but automatically it lights up, and it will then say, you're going at 37 miles per hour. You're going at 40 miles per hour in the speed zone of 25 or 30 miles per hour. And it is able to know that because of this. All right, the radar gun of a police car emits an electromagnetic wave with a frequency of so many, 8 times 10 to the 9 hertz. The approach is essentially head-on, right? The wave from the gun, namely this is the source emits the wave. And this is now outgoing, so they have blue, all right? They show it as blue wave. So the outgoing wave is from the source, and it now goes to the car, and it gets reflected from. Now, when it gets reflected from, it now becomes the new source of sound, of the wave. All right. So first, I have my blue wave. It is at 8.0 times 10 to the 9 hertz. But now, when it hits that car, and that car is coming towards you, and this signal is now reflected, they say that the new, as far as this car is concerned, police car is concerned, this car becomes the source of radio wave, and this speeding car, the source of this radio wave by Doppler effect, is now higher. It's higher by 2100 hertz. All right, you follow what this says? I am sending a wave out at 8 times 10 to the 9 hertz, and now it hits the speeding car, and the speeding car now gives me a reflected wave, but because my speeding car is coming towards me, the frequency now is higher. You remember, because I'm moving towards the source. So therefore, this is now the new source. As far as the police car is concerned, that's the new source. It's a moving source towards it. So it is now increased. The wave, the frequency is higher. And now from this number, you can figure out what is the speed of the car. All right. Are you now able to see the situation? You now know, because you're speeding, the reflected wave becomes your source, that you are now coming towards the police car with a higher velocity, relative velocity, and that now your new frequency is now higher, 2100 hertz. So you can now figure out what is the speed. Well, the book does this here. It's easy to simply remember this formula, the basic formula, and now you don't have to go through all of this. It's easier to just say, now the reflected wave, the frequency, is now higher than the original wave by the original source frequency times the relative velocity, but the relative velocity is now doubled. Why? Because basically, from the point of view of the speeding car, it is now the police car that is coming towards it. And so when you now include the math, the algebra here, it is like as if it is now double the velocity, relative velocity of this car. And when you now work it out, this says you are going at 39 meters per second. The algebra, you leave it to this. I don't like the way Wally Plus does this algebra. I would have done it from the more overview that indeed this now is the guy coming towards me, and it's now you have first this is the relative velocity, but now from the point of view of this guy, you are coming with respect to me, and so the effect is doubled. And you can now say, wow, this car is really speeding, because when it is 55 miles per hour, it's about 24 meters per second. When it's 55 miles per hour, it's about 24 meters per second. But this guy, man, he's going at 40 meters per second. So he must be going at what? 70 miles per hour. All right. But anyway, you get the drift. Leave the calculation, but get the drift of this Doppler effect, radar gun. And one last topic, but we will stop here, is polarized electromagnetic waves, because we use that all the time. The sunglasses, oh, they are actually polarized glass that let electric field in the direction of this polarizer to come through. If it is in the wrong orientation, it will not come through, because if this is my electric field and my polarized glass is oriented differently, it will not come through. And this is the principle behind sunglasses. So anyway, we will meet again on Monday, and we can go into this. All right. Okay, so see you Monday. And by the way, a good advice is, you have been vaccinated, good, but still be careful. You may have been vaccinated, but you can still get the Delta variant, because it's very highly, so just be careful. Don't think that because you're vaccinated, therefore you're iron proof. That's just I'm not a medical doctor. I'm not FDA and CDC, but just be careful, okay? All right, I will now leave and stop the recording.